Hi, my name is Mario Mitchell.
I'm Aquiles Ruiz.
My name is Andrew Lau.
I'm RJ Ascension, and this is our 154 final project. It's an adjustable laptop case. The purpose of this project was to create an adjustable laptop case that would enable users to adjust the posture of their back while using a laptop. This especially comes in handy when the user is using their laptop on the ground, is using the laptop on a coffee table, or just wants to use the laptop in a standing position after sitting for a long period of time. For the kinematic analysis, the initial position of the 4-bar linkage was at 0 degrees. When extended, the 4-bar linkage can reach a maximum angle of 90 degrees. When the laptop is extended 90 degrees, it has a vertical height of 1 foot. It also has a horizontal distance of 10 inches, allowing the user to have a better posture.
For the geometric design aspect of our project, we decided there would need to be 2 links connected to both sides of the base the laptop is resting on in order to support its weight. These links, as well as many other parts of the case, were made using Douglas firwood. To make sure that the links raised in unison, we connected the 2 rear links that support the base of the laptop with a threaded rod. In addition, to ensure the links would stop rotating at 90 degrees, we placed blocks at the front of the case that would not only stop the links, but also act as a ground for the front links.
For the force analysis, we drew up the free body diagrams for each of the links and formulated the equations of motions from those diagrams. By assuming the mechanism was static, all acceleration terms became 0. Another assumption was that the pulling force required to operate the mechanism was 20 pounds. Since there were 9 unknowns and 9 equations, we could solve them simultaneously by putting them in matrix form. By solving the matrix, we obtained the values for the components of the forces as well as the torque.
Since wood is brittle, it will fracture rather than yield. The stress analysis was calculated on the forces that were higher from the results of the force analysis of the 4-bar mechanisms, since this is where the stress will be more concentrated and where most likely failure will occur. The failure of brittle materials under static loading criteria was used to find the principal stresses, maximum shear stress, and safety factor. We analyzed the fracture and compression in links 2 and 3. We obtained a value of maximum shear stress of 3,318 psi for link 2 and a safety factor of 2.52. For link 3, we got a value of maximum shear stress of 7,597 psi and a safety factor of 1.11. For link 4, we consider fracture and tension. We obtained a maximum shear stress of 1,217 psi and a safety factor of 3.44.